Welcome to our second part of the 10th lecture. In the first part this morning, I introduced the concepts and intuition for implementing supervised learning methods as it has been used in GU, Kelly, Ju 2020 in the RFS, Empirical Asset Pricing via Machine Learning. So we went through the concepts of the machine learning approaches, and now in the second part I want to show you the empirical results of that study. I therefore need to remind you on the data we are looking at. Monthly stock returns from 57 to 2016, on average 6,200 stocks per month. There are 94 stock predictors for each, or there are 94 stock characteristics for each stock, interacted with 8 aggregate variables like the dividend yield, interacted with 74 industry dummies, which in total gives roughly 900 predictive signals. In that study, the goal has been to learn the expected return of stock I next month given a machine learning model G that depends on parameters theta and stock characteristics Z. So a characteristic Z for stock I at time t. The learning has been at the first 18 years monthly data. So we're just talking about 200 data points for learning. But the learning is across 200 data points, and for each data point roughly 6,000 eyes, so 6,000 stocks. So we see here we have more cross-section than time series in the learning. Then 12 years are used for validation, and there's a rolling window approach used. So the test is always done for 1 year. So there's 1 year of out-of-sample predictability, and then the training is redone using now 19 years of training, again 12 years of validation, and then 1 year of testing. I've went through these different models. I went very slow, which is why I had to finish the video, the first one, since we went over time. And now we go here to the empirical findings of that research paper. I've promised you a critical assessment. It's important in teaching, in research-based teaching, to highlight from a research perspective what could be done better in the future. So therefore I will mention things which might not be true. I hope they are true. I try my best they are true. But in research, we can only reject hypotheses. We never really know the truth, especially in empirical work. You also see the paper is very well written. It's a top paper. I highly recommend you read it. And as you read the paper, you will notice that my comments here are tangential / orthogonal to the explanations in the paper, or the interpretations in the paper. That's because I take a different lens, right? I take the lens here really for my students, whom I see work maybe in the bachelor thesis, master thesis, maybe even a PhD thesis, or work in a quant hedge fund, in quant asset management, quant research. And I really want to help them to not just explain what the model did, but to pinpoint, to findings, help them build better hypotheses for future research, which they conduct themselves. Okay, let's just get started here. Now here I brought you a table from the paper. It shows monthly out of sample stock level prediction performance. So in short, it's the R squared out of sample. So OOS out of sample, but previously it was just called OS. Doesn't matter here. And it's in percent, monthly numbers. So let's just look. I have, as I always say to my students, I have a lot of boxes for you, collecting the key takeaways. But let's just go to the table. Yeah? We have all stocks. On average, there are 6,000 stocks per month. We said that. Here are the top 30, the top 1,000, the bottom 1,000. Metric is in terms of market cap. So these are the largest 1,000 stocks, the smallest 1,000 stocks. And here we have the percent out of sample R squared for a linear regression. The paper talks and compares performance relative to that quite a bit. I don't do that. That's my first thing I don't do. I just use something which is OLS 3. Why do I do that? Because we know from our class CAPM is nice. It's very useful, very powerful for thinking. But we also know that Farmer-French type of a three-factor model is empirically the better CAPM. So that for me really is like a benchmark model, while a linear OLS with just one factor I don't think is a proper benchmark. So I take this one here. Also in terms of computation, running a three-factor OLS is as difficult as a one-factor OLS. Yeah. So this is what I have. So this is my base case. So you see, if you run a linear regression, a predictive regression, where you use characteristics of the firms, which would be the size of the firm, so like the log of market cap, then the book market of the firm, and here they take momentum. So you see the market factor is left out. This is a CAPM most likely with the market factor. It's not working at all, as you see. So already it's excluded in OLS 3. And what we learn is the benchmark result is you have a 0.16% R square. So that's a rule of thumb which you keep in mind from now on. It means 0.16% of monthly return variance can be explained by a Farmer-French type predictive regression. So it's nothing, but it is 0.16%. But if you come from a science discipline which is not finance, you know it's nothing. Yeah, just visualize that yourself. Let's be generous and really say this was 1%, but it's a 16th of a percent. Yeah, but let's say it's 1%, then 99% of variations is still unexplained. But it's important, go back to my previous part of lecture, it's not because the models are not good enough, maybe, but it's not. Most likely it's because we talked about that in previous classes. Returns are driven largely by epsilon, so innovations in news that are not predictive ex ante. So you see this finance return equity data here is very, very special. Very, very low predictability. So we have a 0.16%. We see large firms have a twice as large predictability relative to the smallest firms. Good. What else do we see? Let's look at the top row here, all stocks. We see that PLS and PCR have a 0.27, 0.26 R square. So what did I learn from that? And here's the elastic net. So let me see what I took from that. This is really my research input for you, my lovely students. We have here, I'm comparing elastic net. It has a 0.11% R square versus the PCR PLS. Now, what I took from that, paper doesn't talk about that at all, but I talk about that here. I'm speculating, but try to be as accurate as I can. What do we see here? We see that we have a linear regression model. Here we have linear regression models with 900 features instead of 3. But let's ignore that for the moment, 900 versus 3. I don't care so much. What I care about is these are linear models which adjust the model on two different dimensions. PLS, PCR has, as I showed you this morning, you are just minimizing the squared error. But with PCR, you are using a PCA on the features, so you're getting rid of feature noise, let's say, and that helps. All else equal, although it's unfair to say it helps, since I have 900 features here relative to 3. But what I want to say is, look, this is an elastic net. It also has 900 features, and it doesn't help. And it even has 900 features plus regularization. And if you have a machine learning class, you come out of the class and you are like, yeah, regularization is what I need. Look at the data here. You see that the regularization and 900 features is not improving the R-square relative to a Farmer-French type linear regression. That is so interesting. That's why I pause. Because you have 300 times as many features. So you can see this marketing pitch of you have more features, you can capture better predictive. You can't. So most likely it's overfitting. The reason why you can't. Now you use regularization to fight overfitting, but you see it didn't work. That's interesting. I think since this is your first real data class in your bachelor's, you've never seen such numbers. So therefore, I really want to spend time on interpreting that the way I see the world. So now I compare that with the PCR, which also took the same features. It did not regularize. So your machine learning class will tell you verse fit, but we see the fit is better, 0.26 relative to 0.11. So it's twice the R-square, although the R-square is close to 0 anyways. I've mentioned that already, but comparing the numbers, it's twice as high. So what's the learning point here? The learning point is for stock returns, lasso, elastic net is just not good enough. You do better if you do a bit of feature engineering by getting rid of the noise inside your features. Unfortunately, in the paper, there's no mentioning on, at least I can't remember, on what's the percent within the variation explained that I cut out. But I just mentioned, I had so many students in the past who don't want to feature engineer, who believe regularization and having an infinite amount of data will do the magic. But in practice, this is what you see. Then you see PLS. It's also interesting. PLS does, in addition, also a PCA on the target variable. I mentioned this morning. Go back. I think it's interesting to follow the entire conversation. It's dangerous to take away movements in the target variable. Although, as I said, I like it conceptually, but it's dangerous because the information we try to predict is a low variance information that we know. And if I cut out low variance components, I just might cut out the predictive part. But what I get from this number, 2.7 versus 2.6, is I did not cut out the predictive information, but I also didn't gain anything in terms of doing it. But I also didn't lose anything. But here my takeaway is kind of the PCR is something, it's interesting. So again, to my students, we talked about the option implied data set we have, this option implied information, which we have for now full trust in its quality. But still, keep an eye on reducing some of the noise in the features. Just at least control it. it might have a big difference. Like you see here, I think the fair comparison is elastic net versus PCR. You're doubling your R square by basically doing nothing, then simply reducing a little bit of the variation in your features. That's really cool. It is especially cool given that the best performing model in the paper is the neural network with 3 layers. And you see they are not far off, yeah, 0.4. So it's less than factor 3, so it's maybe 2.5 improvement relative OLS 3, but this here is maybe a 0.18 improvement already. Still, yeah, so there isn't much that has been done here. Simply linear model, and the Zs are a bit smooth. So the performance of the neural net in that sense is disappointing, but you can only be disappointed if something could be done better. But here, that's a top paper from top researchers, so you can really, as your working hypothesis, assume that it can't be done better given what they have been doing. And what they have been doing had been state of the art. So it just basically says that stock returns have at most, across all the stocks, a predictability of 0.4% out of sample R square. Of course, the paper compares that to the linear, to the one factor OLS. Also, if you compare it to this one, you can say it's a 2.5 improvement, but just in absolute terms, it's just nothing, the predictability in stock returns. But there is a bit, but I think you see what I mean here. Coming from, if you do picture recognition and you have a 0.4% R square, then it's worth nothing, basically, right? That's what I mean. Comparing it across disciplines. Okay, so the other thing you see is the random forest, DAS 0.33. So I did highlight that just yesterday when I went through my slides again, because I started to love the random forest more than I did a year ago. So I would highlight for you as well, understand the random forest well and the neural network and the linear regression models, especially what I've highlighted here. So you see the random forest improves the Pharma French base case by factor 2. But again, I want to highlight, you simply do this PCR thing and you are nearly there. Also, if you look at the bottom 1,000, you are there. You see the linear models really have problems really with the big firms. That's interesting. I've seen that across different tables here. You also see the neural network is nearly twice as good if it's applied to large cap firms, while these linear models have problems with large cap firms. Because for the smallest cap firms, the linear models here, look, PLS, do nearly as good as the neural network and the random forest. Yeah. So I think that's also for you students, I think that's really mind-blowing. It's a pity I couldn't take an in-person class today. I would like to see your face here, because you come usually to an application with neural networks are the best. We have that theorem we talked about, universal approximation theorem. We know that GPT and everything is relying on neural nets and the like. And then suddenly you apply to the finance data. You haven't yet done it, but let's say the pros have done it. And you see for the smallest 1,000 firms, the neural network does not better than a linear regression with a bit of cleaning of your input data. Neither does the random forest, but they do better for large caps. Okay, good. There's a lot to take away from this slide, as you see. Now in the footnote of the paper, but it's on the front page of my presentation because it's important. You know that you have a difference in estimates, but you need to ask yourself, is that statistically significant? So if I were to change the sample, would the numbers still be different or not? So here you get from the footnote that the difference between these two red numbers is statistically not significant at the 5% level if you do Bonferroni corrected standard errors. So we don't need to know what these standard errors are, but the paper in the footnote mentions these would be the proper ones to use, and it's not significant. Wow. Right. Why do I say wow? Because this linear three-factor regression everyone can run. Running these bigger neural networks and the like, many things can go wrong, but you see predictively it makes no difference. We cannot reject the hypothesis that both forecasts are as precise. Good. But the paper could show that the neural net is significantly better than OLS1. But I do not compare OLS1. I think this is really the wrong benchmark. But it's good to know it because it really tells you do not use a one-factor regression for your prediction. Use at least the three-factor one here, size, book market, momentum. Good. So takeaway, feature engineering is important. Regularization is not powerful enough to fight overfitting. Just having a big model like a neural net is having a hard time with equity monthly data to convince us it does a better prediction than if we were to run a simple three-factor regression. I think that's the fair thing to say. And then we also see here already cross-sectionally that there might be a difference in how easy it is for a model to predict big versus small firms, which already tells you here nicely connects back to what I said in the morning with these ensemble models. You see, for example, these guys predict large caps well. These guys do not predict large caps well, right? So if you build an ensemble, you capture that a model might predict one part of the data better than another model, and by averaging you hopefully get an okay forecast for all firms that you might come across. Good. The next thing you see, this is 1 layer, 2 layers, 3, 4, 5 layers. So you see that if you increase the layers, the predictive ability increases. That's nicely, but then strangely it falls. That must be overfitting. Right? It must be overfitting. And I've mentioned that in the previous note. I did not see any penalty terms in the neural net. Now you see how the learning works in our human brain. For linear models, the penalties did not help. I talked about this 5 minutes ago. So I think if their data was published in their code, I would simply want to play around and use a bit of use not the features themselves, but principal components of the features, because it seemed to work here well. So I would anticipate it also works here well. So you see, in the detail, the engineering could be done more precise. Maybe that's something you would like to do in a bachelor thesis or in the project which we offer in the coming winter for every student who takes our financial data science class successfully. Good. As much as I love the table, let's move on. Let's look at the annual out of sample R squared. So first thing you know from our previous modules is the longer the forecast horizon, the bigger the R square. That's exactly also what we are seeing here. Now we see the R square numbers are bigger. What else do we know ex ante? I think that's it. Okay, so let's have a look. So the base case, so the OLS one factor is just really rubbish. The base case here, OLS 3, has an R square of roughly 2.5% across all firms. Interestingly, now it explains the bottom firms better, the smallest, while on a monthly it explains the top better. You see, this is just statistical noise. Statistically, most likely not significant, because I don't see a rationale right now of why on a monthly level, you can predict large stocks better, while if you take 12 months, it's the opposite. So it's just statistical noise within these small numbers anyways. So therefore, let's keep looking at the top row only. I try to focus on that one. So we have a 2.5% benchmark R square out of sample. Okay. Now, what's our random forest doing? 2.38, and neural net 3.6. Yeah, so in the paper it says neural networks win. But again, there is no statistical test, at least I don't remember, in terms of being statistically different. But I bet €1,000, 3.28 and 3.60 is statistically not different from each other. So therefore we see random forest neural nets, they do as well. We also do neural network with only one layer, and these 32 neurons is not doing too well. It's nearly as good as a regression model. That's interesting. If we had more time, or you do it at home, compute out the number of parameters you have here relative to here. Here you have 3 plus the bias, 4 parameters. Okay, I do the calculus myself, I'm so curious. And here we have 900 features times 32. It's huge, yeah? And then plus the bias. So let's be generous, 1000 times 30, it's 30,000 parameters. It's ridiculous in a way, right? If you think about, you have 30,000. In terms of computing power, what it takes, and the smartness you have to put in order to not be fooled by randomness, and it doesn't really work. It doesn't really perform better than the OLS3, even not for small or for the top, for largest firms. If you have 2 layers, it doesn't work better. 3 layers, yeah, at least you have 3 in front of the comma, but statistically speaking, most likely this is also not different than 2.5. So it's interesting, yeah. If you have 3 layers, we had this last week in the class. How many parameters do we have? It's multiplicatively, so we had 1,000 times 30, 30,000 here, times, and now we are multiplying again, times 16, so let's say it's times 20, it's like 600,000. Maybe I have a 0 wrong here, and this would be like 6 million parameters. I don't know, it's ridiculous, but you'd see it doesn't get you anything. Now, I don't talk like the paper does, it's important. I say I do my interpretation for my students here. And if you have your Python, your bachelor thesis already, you know, or you want to do your predictive exercises, you have to think carefully whether it's really worth the pain. In terms of R square, that's what I'm saying here, is in a statistical sense. The numbers are bigger, but statistically it couldn't be shown that they are significantly bigger. We later look at portfolio performance, that's the second metric. But in terms of statistical accuracy here, there's not much bang for the buck. We also see NN5 does worse than NA4, so it's overfitting. Yeah, so the networks in the training are not able kind of to overcome this overfitting. Again, we see maybe it's regularization missing. Coming to regularization, also it's beautiful here. We have regularization 178 versus no regularization, but therefore regularizing the features using PC, much better. So here's my punchline for you, my lovely students, that it's the regularization of the Z which is much more important than regularizing the parameters. I hope my PhD students look at that as well. I need a flag on the video here, because this is very, very important, because we tend to learn from the textbooks that regularization does the job, but we see it doesn't. For equity returns here, it doesn't. It performs worse than if we were to work with OLS3. So it's clearly saying regularization doesn't work. Because the theory says you take your 900 features, regularization works, using the validation set, everything is done properly, you do better, but you just don't. Yeah, so you're really destroying predictive information by simply adding features. that's now a statement to my PhD students, because the other paper I'm talking about also, it's 3 years ago, has this when you read the paper, it's about let's add as many features as we can and machine learning will figure it out. But you see, it doesn't necessarily. And the recent papers more books I'm reading in the computer science area of machine learning, it also states you don't want to add redundant information. You don't want to add features which are not highly informative for the prediction. And that's what should be our base case thinking. And here's the evidence for it by example. 900 features relative to 3, we are halving our R-square, although we use regularization. Now, in contrast, if you want to work with 900 features, do a bit of feature engineering. Yeah, if you engineer the Zs by getting rid of some of the noise in the Z, you are increasing the R-square by roughly 25% relatively to 2.5. And here, interestingly, if you are using PC on the Y, it doesn't help. But of course, statistically, it's not different from each other. But if I look at the face value, it doesn't help. So it's a good learning for me, because I asked myself yesterday evening, would I want to get rid of some of the variation in the target? And I would be careful to do that in the future, but I would like to have a control on controlling the amount of variation in my features. That seems really to be of first order importance. It's more important than going with bigger models. I mean, this paper here doesn't convince me. If I look at results to go bigger, I think it rather convinces me towards feature engineering. Which, again, for my PhD students, it is interesting, because 2 years ago we had a very capable computer science student, and he mentioned that feature engineering has been used in the past, but now it's not that much anymore, blah, blah, blah. I say blah, blah, blah because different resources say different things. I have read recently things which are pretty strong on feature engineering. And it's just this full intuition coming back to the regression. If you are regressing something on X and X is noisy, and you have a way to reduce the noise without getting rid of the information, of course you do it. So I really love this section here. I love the table for the transparency reason, and I hope you also love what you can really take out of these numbers, which usually you don't, right? You just see 178 is different than blah, 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 but I really try to add the intuition as much as I have it to help you build a better model in the future and a better data setup. But it's a great paper. I mean, that needs always to be stated. But it would be even better to the authors if they did publish the code and the data. I mean, it would really help the community to move forward faster. Okay, so this is great learning here. Awesome. Okay, again, 3, 6, 2, 5. Most likely it's not statistically different. Good. Now I'll talk about variable importance. Now in OLS3, it's a plain predictive regression, and we have size, book market, momentum as the predictive. There's no further information provided. It's a pity. Standard errors, t-statistic, the like could have been provided, but I would assume most likely all of the threes are significant. Just take it from here that the R-square is pretty high relative to the best performers. But of course, seeing it in the data is more than just guessing. Now let's look at the neural network 3 layers. So that was kind of the winning model based on 1 month ahead R-square. And here it's also not in the paper, but I must have taken the data somewhere. So it is in the paper, of course. It's a graph from the paper. This is what I've done. So it's variable importance. So I haven't talked about that previous class. So, but if you do research on that, you would learn that by doing. We know OLS regressions, MLE, we compute standard errors, t-statistics to talk about the importance of a variable. Or we can leave a variable out and then check how does the R-square change? Now for neural networks, they use a different approach. So let's just, without going how the approach works, go a bit to the punchline of it, since it's a bachelor's financial data science class, so we don't go through all the analytics, only the ones I think are of first order importance. So what is important here? If you just had one variable out of the 900, then you would pick 1 month momentum. It's also called short-term reversal, and that within their metric of importance captures already 22% of the information in the prediction. Maybe that's the way I could frame it in easy terms. So why do I like that? First you see it visually, and now you see it in terms of numbers. I took the number from here, most likely 22. Now my caution thing for you is having more features is not better. I try to talk less like a scientist, like a German professor with, it depends, it could be, one has to, I just try to be more like a trader. So it's easier for you to make mental notes. More features are not better. We saw it here. More features are not better. We also see overfitting, which is one reason why more features is not better, but another is that features correlate with each other. So here I already see that one feature alone captures 22% of importance. Yeah. So if I take a bit, although it's not a PCA, but I understand PCA. So I know that if I have a 22% importance, that is pretty major, because it means the other 899 variables capture 78% of variance, of importance here. It's not variance, it's importance. Yeah. So one factor is important, it's momentum. Yeah. And interestingly, momentum is in the regression, while in Pharma French, it would not be momentum, would be the market. So therefore, I'm really thankful for the authors to add momentum into OLS3, because it would have been tempting for them to put the market in here, and then OLS3 would look much closer to OLS1 than it does to these guys. So that's really great. Yeah, it's a top paper, as I say, top researchers. So it's really nice. So momentum is important, and you see here the linear model already captures the momentum predictability into the stock returns pretty nicely. The next thing which is important is log market equity, 11%, so that is size, also part of the linear regression already. So you see, just by running a Pharma French type regression here, you capture already, in terms of importance, a third of what you could capture. And that is really mimicking what we see here, that this 3-factor regression is just doing great relative to this highly parameterized neural net. Yeah? So there is a lot to learn from that. Yeah, it's like, I've mentioned that in previous classes, you have some information mu, which we try to learn. And if you learned it, you learned it. You will not learn more if you add more features, more parameters, more twists. It applies to stock return data, which what I refer to here, of course. The next third important, nearly as the second, is return volatility. So that'd be interesting if there was an OLS4 model, which also includes return vol, because there is literature which uses return volatility as a factor. That would be really interesting. So I have the feeling we would get close to 2.8%, 3%, which would be very competitive. I mean, it's already competitive, but maybe we would even, the question is, can I come? Okay, now I'm doing too much data mining, so I should stop that. Then we have max return and momentum, the change in momentum, 6%. So 1, 2, 3, 4, 5 factors alone capture already more than half of the importance. So my thing for that's then for the PhD students. But of course, the bachelor students also highly benefit from my very pointy and controversial way of presentation. Is first, accounting information does not matter. Yeah, that needs to be a yellow marker. You see there's no accounting information in the top predictors. Even here, if I don't see any accounting information. So accounting is dead, has always been in our course. You see, we never talked about it because it's not relevant on the average across these 30,000 stocks. Yeah, Warren Buffett, of course, checks accounting, checks balance sheets. He looks at firms specifically, individual firms, but here law of large number. Prices are efficient, markets are efficient, it doesn't matter. Everything we need is in the prices somewhere. Next thing we see, I claim that smaller, more parsimonious models are likely, I would like to say, more successful. Here it says as successful, but I think I can get rid of the likely here, because of course we see they are as successful. That's my discussion here. But I want to say even now they are likely more successful because of my discussion here. Yeah? If there was a feature engineering done before moving it into these nonlinear models here, I think it would perform better, as I've discussed. I see it from the PCR relative to the OLS3. Likely more successful. I mean, these guys, they are clearly as successful, but more successful. Okay. And option implied information, you wonder, it's not part in the analysis. Yeah, the paper was written 2018. I've mentioned to you, that's why we also cover option implied information. This is new. This is something when you go to the market, to the internships, to the jobs, to your thesis work, your counterparties will not have any / much experience with option implied information. And you see it in that study. They just ignore that information completely. So what I would have loved to see is you take the top 5 here and you also rerun the analysis just with options, take the top 5 there and then put these guys together and then kind of figure out how important they are relative to each other and with each other. And again, if the authors did publish code and data, we could just do the analysis very quickly. Otherwise, it takes some time, and therefore we don't do it, which is a pity for the entire academic community in this field, in my view. And I think I say that since I take these computer science classes, they talk a lot about enhancing the community, sharing, and the like. So I think we have to do more in finance on that part, if we want to grow as a community. Good, but option implied is not there. So if option was there, I would think it would at least 2 option factors would make it among the top 6. I have the hypothesis. Good. Now with regard to random forest. Why do I do that? Because the paper doesn't talk about that much, so I've been thinking about it. I would find it very weird if the predictive signals are different in a model which is also doing very well, but which produces a different forecast, because it's weird. Yeah, you could say, why is it weird? Maybe it correlates with another feature. Okay, that's okay. I get the point. But although we're just capturing correlation, at the end of the day, it's an econ subject, so we want to think about causality in the long run. We want to think about theories. So the good news is we have similar top performers. Yeah, momentum was 22% in the neural net. Here it's 12%, top performer also. So we see there is some similarity here. We also see dividend yield matters. That's nice. In our case, number 1, very first day of class, 3 months ago, we had the dividend yield be a predictor. You see, really, it shows up even inside the random forest. So it is a predictive thing. The log market, that's the size from Farmer French, max return, we saw it previously. Yeah, and then you see there are other factors which are important. but the importance is only 4%, so there's a big gap here, 12 versus 11. So I usually am pretty generous, so I would say that doesn't matter much here. I have the feeling there is some variable missing, which is most likely putting these guys to 0 if you were to include them. And I see here return vol, momentum, yeah, so maybe if we have some option implied volatility and the like, I can get rid of all of these guys here. So I have to say this I like with neural networks better, that I have more like an exponential decay in the importance, while here I have like a mixed factor back. I don't know how you will think about that. I like it better if it really decays exponentially. So these guys seem important. Dividend yield, momentum. And keep in mind, random forest is not performing better than the OLS3, which has momentum in it. Dividend yield is similar to book market. We talked about that, different quantities for value. We looked at this old Cliff Asness paper where he also says this the type of fundamental factor itself to proxy for value is not important. So I think dividend yield is like book market here. Maybe it just gets driven out because they're highly correlated. So again, we have momentum and value which matter, which is exactly what OLS3 captures. And therefore the forest with the nonlinearities can't do better. The paper is different on it. Paper is arguing the nonlinearity matters a lot and the like, and has evidence for it. That's why I said I will do a very critical assessment to my students here in the way I interpret things. I'm not as qualified as these top guys, but I try hard to catch up. So I think it's like an ensemble forecast. Read their argument, listen to mine, and make an average of these two things. Good. But the good thing is, roughly speaking, the feature importance random forest neural net is along the same lines, which is good for me. Otherwise, I would have several warning flags. Good. Good. Interesting now. Now we move. Now we go away from the statistical predictability towards the Sharpe ratios. So we talked about Sharpe ratio when we talked about CAPM, markowitz. So it's a measure of outperformance, risk premia relative to volatility. We saw it's the key metric for Markowitz optimal portfolios. And now here's the increase in monthly Sharpe ratios relative to buy and hold. So here's the interpretation first. If you do OLS3, so in a way my favorite, in terms of teaching, and if I had to run my fund here, it's just easy and nearly as good. But you see now, if I do OLS for timing, meaning I run a prediction and then I do a long-short portfolio based on I go long the firms with the highest expected returns, I short the one with the lowest expected return, with the negative ones basically. I can generate a Sharpe ratio which is 0.07 points higher than if I just buy the S&P 500, buy and hold. We see a picture coming up. But for now, look at the table. So that's like the base case. Yeah, I do 0.07 better. Is that much or not? I don't know. Practitioner said it is a lot. For me, I don't think it's a lot. If the Sharpe ratio on average in the market is somewhere between 0.345, 0.6, yeah, let's say 0.6. So I can increase by 10%. Is 10% a lot? Practitioner says yes. I say not so much because I know there's a standard error around the estimate anyway. So, but these are the numbers. Now, interestingly, you saw I was strong on PLS and PCR in terms of R square, and I was weak on elastic net. But now, interestingly, elastic net does better in terms of Sharpe ratio. This is really weird. It's really weird because we have now a scenario where the elastic net does worse in terms of predictability. Let's look at the monthly. It was not that much worse, but still worse. But in terms of Sharpe ratio, it certainly does better. So to me, it looks like statistical noise. I can't remember having read in the paper whether or not these Sharpe ratios are significantly different from 0. I just read that it's a major difference. And usually major is related to statistically significance, but you tell me, I should check again, but I don't have the time to do that. So I just say it was not checked. Again, this R square I took from a footnote. So I'm already reading the footnotes. I can't remember that. So I think this is statistical noise here. And you see, my students, you need to be critical. But not just be critical, but try to find a line of reasoning with data and with the theory behind it. Yeah? So again, we see high R square, or we see higher R squares for the PCs, low R square for elastic net, and suddenly elastic net does better in terms of Sharpe ratio than this. This is just weird. And weird just means we don't understand it, and we try to understand. So that's, I don't understand it as of now. So maybe it's just random noise. So, but the punchline is higher R square, that's something to take away for you guys. Higher R square does not translate to better long-short portfolios. That's interesting, because my thought was the same some time ago. If I have a higher R square, I predict better, so therefore I should have a better long-short portfolio. But this is not true, as we see in this example. That's interesting. So that's something I think to better understand. I already did the interpretation a bit for you in my thinking. It just means that this long-short Sharpe ratio, which we are computing here, must draw from the predictability of the short versus the long, and that's something to come in the picture. I don't think this is meaningful to you right now as it stands here, of the short versus the long leg, but it will come. There will be a punchline, I show you that in the graph, is that the long short really benefits from the worst expected performers. So therefore it's not universal across the 6,000. It's really a specific part of the data that you take short, and therefore you're really improving. And why do you suddenly perform better on these? I don't know yet. Let's see for the table to come. If not, that's not explained in the paper. So what else do we see here? We see the neural network has a 0.26 improvement in absolute points. So maybe that's a third of the overall Sharpe ratio, I would think, if it's 0.6, 0.7. Random forest does 0.18. No reporting on statistical significance, which is a pity, I think. But I think it's not reported, meaning it's not significant. And everyone who has plotted realized Sharpe ratios know they are volatile, and therefore these numbers here, a third relative to average, is not much, given that the volatility is really large of these Sharpe ratios. Yeah, so it's not significant, therefore it's just noise or inconclusive. And it's interesting, if you go back to my first part today, again, it's for my bachelor students. I've highlighted we only have 200 data points for learning in the first learning run, with 18 years, 18 times 12, roughly 220. And you see, inconclusive. It comes from not having infinite amount of data, and not even close to infinite. Good. But if you read the paper, read it carefully, you see they talk about being a massive improvement in Sharpe ratios. So I would be there, I'm very German, yeah, I would be there more cautious. It might be massive, but so far the significance is not reported. And it doesn't seem big to me as a non-asset manager, considering the noise around the Sharpe ratios. Good, yeah, okay. So, monthly machine learning portfolio statistics. Now I have another table from the paper, so I added some color. So I look at my base case here of the paper, OLS3, momentum, book market, and size, linear regression, and then the neural network 3, which wins on a monthly basis. Now what the paper here, let me give you the highlight first, then the details, and then the highlight again. Now the highlight is that, and that's what I found out kind of by looking carefully, the key improvement of the neural network 3 in terms of this long-short Sharpe ratio here, which we don't know it's significant or not, so it's not significant, is it's able to predict the losing stocks. So let's say you have 6,000 stocks and you have 6,000 predictions every month, and now you put them into decile portfolios. You see how well our problem sets work in the class. You already finished a problem set on long-short portfolios on a large data set. So there are only very few bachelor students who are going through such problem sets. So it speaks to the course, to our PhD students who help. Thank you so much, guys, and to the KIT and my students for the pleasure of going through that. So you have 600 stocks per decile portfolio, and you see that on a high level still, OLS and neural net provide the same Sharpe ratios across 9 out of these 10 decile portfolios. Therefore it's as good, which is confirming you won't get statistical significance most likely, because it's just one decile portfolio which is responsible for the neural net creating a higher Sharpe ratio. Otherwise it's basically the same. So let's just see. I took the median bucket here, 5. So this is like a firm whose expected return is not top, is not negative, is somewhere in the middle. So somewhere normal market conditions, a normal firm, I think like 8 to 16% expected return annualized, something like that if we were to on average. And you see that the predicted expected return is 0.62% per month. So if you multiply by 12, you get like 8%. You have an average realized return of 0.8. So annualized, it's roughly 10%. So everything according to textbook. There is a standard deviation of 5%, which already tells you that Sharpe ratio has a high standard deviation, and therefore it will not be significant, what I said previously here. Here we have kind of the confirmation. And you see that the realized Sharpe ratio is 0.6. Now the neural net for such a median firm has a Sharpe ratio of 0.5, even lower. And if you go and look at the fourth decile, neural net has a Sharpe ratio 0.49, OLS 0.57, better. OLS is better at 6.3 versus here 5.9. So you see, if a firm is some average firm, so something you would pick by accident, I argue, you do as well with an OLS in the machine learning Sharpe ratio setting relative to a neural net. The neural net is really shining. If we go to the high one, it also doesn't shine. You see Sharpe ratio is 0.79 with OLS. It's 0.8 with the neural net, so it's exactly the same thing. It does really better here in the lowest decile portfolio. So the OLS has a problem. Let's say 6,000 firms, so roughly 600 firms with the lowest expected returns are predicted to have a 0.17 return on average, but the realization is positive. So you are shorting a positive return asset, which is of course a bad thing. But what does it tell you already here? And there's a figure to come, but it tells you already, and I want you to learn this reasoning. That's why I also take so much time for this presentation here. It already tells you, if you do a long-only portfolio, what most of my students will be doing, there is no need to go with a neural network. But it's important to take the proper feature for your predictive regression. And based on theory, we came across this OLS, far more French, but here it's a bit twisted with the momentum factor being in, which is important, right? But if you're long only, just do an OLS for your retirement fund, basically. That's the way you should go. But for a hedge fund who goes long-short strategies, they really want to short stuff. They should then deviate from the OLS, clearly. Because interestingly, their prediction for the lowest is close to 0. It's also interesting. It's really not negative. So it really tells me the linear relationship here has a problem, because everything here is linear, and therefore it just translates it back to linear in the negative, which is not good. But if you have non-linearities, you can have like this convex shape that from something which is falling maybe linearly here, then it's more like decaying in a convex shape. But the bottom line is, on average, you have a minus 3% prediction, and then the realized return is even lower. It's minus 0.4. Yeah, so they get the direction right. That's the key. And therefore, they have a standard deviation, a Sharpe ratio of minus 0.19, and that's the difference. Yeah, because if you look at even decile 2 portfolio, the Sharpe ratio of the regression is higher than of the neural net. So just to say it, oversimplified, the neural net doesn't work in 9 out of 10 portfolios sorted on expected returns. But the neural network works on the lowest, so therefore on a H high minus low, it overperforms. So I think this already tells me if we use like a Markowitz analysis, which we had in our class, so you make a prediction for expected returns and then you put it into Markowitz, I would argue neural network is not worth doing it. If you do it correct, it's still not worth doing it, because in the Markowitz you would usually not short stuff. And if you do it as a student, you most likely make mistakes on the way. So I wouldn't do it. I mean, it's not me. The science statistics says OLS is good enough for Markowitz, but for long short, it matters neural net. So you can really see that if you do a long short, the Sharpe ratio you get with OLS is 0.6, but you can double it. And this is the punchline of the paper, a little bit. But now I dissected it really hard, where this improvement comes from. And still, look at the standard deviation, it's 5. So if you think about a confidence interval, most likely this stuff is not significantly different from each other. Okay, but it's a wonderful table, so it's great to really dissect that so deeply. Here is now a graph representing the time series of the previous table. What does it do? It shows the cumulative return of these machine learning portfolios for the long lag and the short lag, because it's a high minus low performance of NN3, for example. Yeah, this guy here with the 1-to Sharpe ratio. Let's look at this graph, high minus low. So you go long, high prediction assets, and you short the one with the lowest. In the graph, this would be the red line. So you see the high part, what you go long, has this performance. Here you have recessions. And then the short part has this performance. Let's say here -3, but you are shorting it, so it contributes +3 to your high minus low portfolio. It's also interesting here now that if you look carefully here, it's kind of flat since 2003. While this guy keeps rising. So again, it shows me the high minus low is really driven by the high after 2002, by the long only. But prior to 2002, the short lag did contribute equally, both at roughly 3, while then it goes to roughly 5 and this guy stays at 3. So therefore it's kind of dead. So I wouldn't invest in that, I have to say, in the short lag after here, but I would keep working in the long lag, which is still telling me long only and OLS, it's basically as good, considering the complexity and the statistical noise and the estimates. Now let's redo that for the OLS3. You see the long lag is here, it's pretty competitive to the neural net and to all the others. So where did it lose? It lost here in the early, and let's say up to 2005. It kind of made up a gap, then it stays kind of constant. But long only, it's kind of, I think it's good enough for most investors. But you see the short lag would be the dotted turquoise color, this guy here. Yeah? You see you're shorting positive firms, so better don't short. And also here you short, and on average you are shorting positive firms, so I wouldn't short at all. I think what I take from it as an investor myself for retirement, I repeat that, but this graph is confirming it. Run an OLS with these proper 3 factors, long only, do timing of the market, and you improve the S&P by 7 Sharpe ratio points, 0.7 points. It's not enough for me, so I don't do it. I would still keep buy and hold the index. So you see, bachelor students, how I now, without saying, relied on Markowitz, efficient markets, there is no alpha, these type of things, when I say it's not enough for me to really start to do active investments. And for the hedge fund business, I think this is really worrying. I should put that on the notes. I just forgot. Just see it now that I used so much time to discuss it. There's really nothing what the short leg is contributing to. Of course, during the crisis it does, which is a good thing. So, but overall, unconditionally, in this later part of the sample, it doesn't do anything. And you've been to my symposium with the industry guys, and you remember presentation of this one German hedge fund where it said pharma French factors are kind of dead after 2000 and was it 8 or something? So we kind of, what do I take from that with they are dead? I see there's a premium still paid, which it should be according to CAPM. There's systematic risk, which pays a premium if markets are risk averse, which they are. So therefore there's a premium which we see here, you get by long only. Long versus short, it's about can you time them, not about timing, long short, can you exploit differences in expected returns. So far we've seen it's very difficult. Statistically it doesn't work basically, what I take from this study here. We also see it visually here. If I take an ensemble, if I just take the average across all these models in the short leg, they're kind of all flat. And even they are flat. If I take the average, they're completely flat. So really the short leg doesn't do anything. I would not invest in that. If I was a fund of fund manager, I would rather focus on the long. And the black, I think, is important. That's the S&P 500. That's the market. That's interesting if you just invest in the market. So I think to the question whether the Sharpe ratio 0.07 is important, well, it is. I think that's my additional learning point. This number doesn't look much, but if I look at this one here and the scale, cumulative returns, I would tend to think this would be 100% here. It's 87, 97, it's within 10 years. It takes roughly 15 years for 100%, which kind of makes sense, like 7% per year. So we really see we overperform the market. That's, I think, the key statistic here. So let me add that for next generation. Short leg is dead since 2002 across all models. I think that's correct. And long only dominates buy and hold SP 500. That's also a key takeaway. Because I have to revise my statement from previously. My statement, we know from CAPM, Markowitz, you just hold the market, you can't get more, right? Let's assume they all have the same beta exposure. I would kind of assume it is, since they are diversified portfolios. But you see it makes a difference. You end up here with 200% in the market, while if you do some timing, you get to 500%, or with Pharma French to 400%, which is a different factor too. That is good. That is good. That I like, I have to say. I really like that. Because running a Pharma French 3 is very easy. And then building a long-only portfolio is easy. So you just invest in the naive diversified portfolio, but not across all stocks, but only across the ones with the highest expected return. So why not? I don't see any problem with that. And I would double my my realized return relative to buy and hold of the index. And if I do neural net, I do a little bit better, on average. I go from 400% to 500. but I would not do that. This is a 25% improve. 1 in 4, a 25% improvement over 30 years, which is worth nothing, I think, on an annual basis. That's why they are also Sharpe ratio wise not different on the long only, and it's far too error prone and statistically not convincing to go this extra mile here. So I hope students, you follow that precisely, because that, I think, is really cool thinking and intuition if you were to work in a hedge fund or in an asset management firm and you have to decide whether or not to do something. So catch up with me if something of that is unclear, or if you have a different opinion, then we will talk it through again. Yeah, that is what I've overlooked here. I should really highlight that, since I'm running out of time anyway. So I think let's just make it extremely precise. I think this is cool. And this is cool. This is cool. And this one is cool. Yeah. This one is cool for the market, just to highlight for future generations. This is a 2% spread. No, it doesn't shorten. Oh, shoot. Okay, let's just leave it like that. Long auto we know it's in Klammern X4 versus X2. Yeah. No, let's maybe say more placatively 400% versus 200%. So that's the difference. That's the difference. Okay. Awesome. Okay, great. I'm running so much out of time. Both lectures would be over. I only have one. So it's by accident I cannot be in class. I think it's of benefit, because I could not have spent so much time, but I loved this interpretation. I really want to share it with you. And I'm also taking extra time in another class if my bachelor students want to. I think it's one of the rare occasions where we can really dig into these numbers with lots of understanding given our prior modules in this bachelor course. And let me just summarize. Now, in the research study, they use monthly equity returns for in total 30,000 stocks, on average 6,000 per month. That's because firms drop, and some firms go bankrupt, so they're not on the exchange anymore. It's since 87. Now this is my summary, not the one of the paper. So for a long-only investor, OLS3 is all you need. I'm even more bullish now than when I wrote that, given the analysis we have done together, or I've done now for you. If you are for long-short investors, the neural network might improve performance. I say really might, since statistically it wasn't convincing that the overperformance is significant. But of course, if you look at this last chart, no. Even if you look at the last chart, let's be serious again. In the last chart, we clearly saw after 2002, the short lag did not contribute to performance. It was flat. Okay, that's why I might. Yeah. The relevance of the 900 baseline features is very questionable. We saw that when we looked at the PCR versus, no, we looked at OLS3 versus PCR versus neural net. We had a long discussion on that, and I could not get convinced that adding 900 features, I have no problems with the features. I have problems with the resulting 100,000 to millions of additional parameters, which can't be properly estimated. Then again, to my students, I highlight that we have so far in the literature no presentation of standard error t-statistics and the like. So I can't really pinpoint and say this guy is completely overfitted here. I really have to go the route as I did, looking at the output very carefully to figure out it's not well identified, the parameters. But based off first order regression type thinking already, and I mentioned that over the past couple of classes in person, that just bigger is not better. According to this research paper findings. Okay, another takeaway is feature selection is important, more important than specified in the paper and in most machine learning courses that you attend. Let me know if there is a course which highlights that, and I would want to take the course myself. But I could just see from the output here that less than 20 features seem to be sufficient. So I would have loved if the authors rerun everything, maybe using just 50 features. Yeah, kind of. Of course, you could say this is now data mining and the like. So I think one can make a research setting where it's not data mining. So maybe it is data mining. So I think therefore the punchline should really be, it makes no sense to just, because I think about our database we have at the chair. So we have like thousands of features, but it just makes no sense to push them all in and cross fingers. It will not work. The results will not be statistically significant. If we run simple kitchen sink approaches like this one here, there is not sufficient information in the data to identify these highly parametric models. So the punchline was here, less than 20 features seem to be sufficient. We saw that in the importance decomposition, and we clearly saw that in the OLS3, which performed so well, both in terms of sharp ratio in the long only, and in terms of the R square, and it just has 3 features. So give me the case why I would need 900 features. And I think the paper gives the case without stating it that you don't need these 900 features. But you need a way to make feature selection. And we learned that from the paper also that the elastic net regularization is not strong enough for the feature selection, it doesn't work. So either they have a problem in the validation, that the lambda grid is too coarse, you know, that they are not penalizing strong enough, or it's simply, it has just been applied to the linear models that, what do we know? We know, it was summary, I take away from me, the OLS3 performed better than the elastic net, which shouldn't be in theory. So I think that the takeaway is really the data, even though it's 6,000 stocks times, but that's why I didn't make a joke when I said just 200 data points. It's simply not sufficient, the data, to identify the loadings of these 900 features. Otherwise, the PCR and the elastic net should have overperformed OLS3, but didn't. Yeah, because in theory they should. In practice, they didn't. So therefore, you see why I mentioned a while ago, we, in our chair, so therefore if you write bachelor thesis, master, PhD with us, we go a different route, right? But we learn from these guys, so we are very, very thankful and highly respectful to this excellent work. But the point is, we need more time points. And while this article also from Kelly about it's a low data environment asset management, I disagree. This study is low data environment, but therefore we have to go high frequency. And we have several studies right now with our students who work on that. And then it's about what I have here. I don't think it makes a big difference if I have, let's say, 5 top factors like momentum, so on and so forth, and then to add 2,000 questionable factors. And with questionable, I mean there's no theory of why some factors should matter. That's why I come to the option implied. We run research ourselves yet, and we are agnostic about the findings. So we are going to present what we find to the community. But for option implied densities, at least we have a theory of why it should matter. Because, and that's why I took it into my bachelor's class last 2 weeks, but I don't have videos for that, unfortunately, since we had a lot of Blackboard work. But just on a high level, options allow us to extract the density of the underlying that the market prices in. Now, the market is smart on average, and therefore we can extract a smart density. And if information of that density matters, like volatility matters, there is CAPM extensions of why variations in the variance of the market, for example, matters. There are theories of why the skewness should matter. So that is really very sound. And the good thing is, and if you're interested in research, get in touch. We have these densities at up to tick by tick frequency, which is a blast, right? Because we could just rerun this entire analysis here if computationally feasible instead of 200 data points with 1 million data points easily. So yeah, therefore I'm very bullish on this research field. I think we need more community sharing, that the development time is faster. Like we do a lot of data engineering, which we would be willing to share, and it's great if others share the machine learning infrastructure, so we just bind these things together, because the big problems we have are much, much bigger, right? I think the big problem is something like large language models in real time on a tick by tick level. I want an answer which is precise, and it's the same the way I think about machine learning portfolios. I want a tick level. I want to know what's the risk of my portfolio, what's the expected returns of the portfolio, what are the risk factors of the portfolio, what should be the portfolio weights, and I want the action to happen. And with the data, we are working on that. And with the algorithms, we need to really run big data tests. Yeah, while this one is a rather small data test relative to the comparison I just gave. But overall, it's a very useful paper. It, for good reasons, sparked interest. And not just the interest was always there, but it was really like, since these are the top guys in the field, it was saying now everyone jump for it, which many people are doing. And I tried with my discussion here to give the bachelor students, which is the very new generation, as honest as I could and as critical as I could, but still fair and respectful, an assessment to help you do your thinking once you are without me, right? Once you are alone on your own feet. And you see, I hope, once you follow that, the findings can really be put into perspective. And it reminds me what Andrew Ng from Silicon Valley said in one of his old machine learning lectures. He said when he went to Silicon Valley as consultant, he saw immediately that predictions will not work out, where then the industry guys will spend, he says, 3 to 6 months on testing, validating to find out it doesn't work. And I think something else happens here, and I try to help you with contributing towards you building up that intuition. Good. I will stop this part here. I will still record the third part since I want to present you everything. I can already tell you there's this upcoming problem set where we give you simulated data and ask you to run like algorithms that have been done here with the same statistics. Yeah, so random forests, neural nets, the elastic net, and you run these different comparison statistics and the like. But we give you simulated data with a high signal to noise, so you will have high R squares when you do the exercise and the like. But it's just about like when you learn the multiplication table, that you're just able to run that in Python and figure out a little bit how to do it and the like, do some research work in a safe environment. If you really want to do something bigger, then I invite you for our research module, which we are offering to the bachelors, and of course different types of thesis work coming up. So thank you so much. I think it was a very important lecture. And we have one extra lesson in the last class. We either do reinforcement learning or if you want, we just come back here and discuss as a team. Okay, but for now, thank you so much.